Hello everyone, welcome. In this video I will solve a simplified attack lab example. This is the function we need to call in level 1 of this example. As you can see, we don't need to do anything fancy, we just need to call this touch1 function normally. We need to start by disassembling the executable file we have been given. We can do that using objdump command with -d option. Now let's inspect the disassembled code. We need to locate the getBuff function, which has a security vulnerability. As you see here, the function first creates some space for the buffer on the stack, and at the end of the function we see that it removes this buffer and returns. This means that following the buffer we have the return address. We can overflow the buffer and change the return address. So first we need to determine the size of this buffer. It's given in hexadecimal here, but we need to determine its decimal value. We can use Python for that. The buffer size is 72 bytes. Now we can craft our exploit string. First we need to fill the buffer. This is called padding. There needs to be 72 bytes. The values don't matter. We have filled the buffer now. The next step is determining the new return address. Let's open the disassembled file and determine the location of touch1, which we want to call. The address of this function is given here, so we will use that. But our architectures use little endian notation, so we need to reverse the order of the bytes here. First, we need to separate this address into bytes. Since this is hexadecimal, each character represents 4 bits. So we need to group these characters 2 by 2. And now we need to reverse it so that it's little endian. Our exploit string should be ready now. Let's try it. As you can see, it worked and we have successfully completed level 1. This is the function we will call in level 2. This time we need to pass an argument, and that argument should be equal to our cookie value. In order to do this, we need to resort to code injection. This was our solution to level 1. I will use it to demonstrate the fundamentals of code injection. The basic idea is that we include the assembled version of our injected code in our exploit string, and in the return address, instead of giving the address of a function in the program, such as touch1 in this case, we will give the address of this buffer, which includes the injected code. We will need to figure out the location of this buffer later. For now, as a simple example, let's say that our injected code contains a single instruction, and that instruction is return, which is denoted by C3 in hexadecimal. Now, since we have added 1 byte of instruction here, we will need to remove 1 byte from the padding, so that the location of this return address remains the same on the stack. In the next step, we will figure out the location of this buffer. We can use GDB for that purpose. Let's load our program into GDB. Now let's put a breakpoint at getBuff function and run the program. We can use disassemble to see where we are. And since we are at the start of the getBuff function, the memory for our buffer hasn't been allocated yet. So let's take a step and let it allocate the space. Now the RSP pointer should point to the start of our buffer. Let's print the contents of the RSP register, and this should be the location of our buffer. Let's copy this, and we will update our exploit string with it. We need to remove the leading 0x, and also we need to reverse the order of the bytes here because of little endian. Also, the return address should be exactly 8 bytes. Therefore, we need to fill the remaining bytes with zeros because they represent the larger digits. Now, when we execute the program with this exploit string, the program will return to injected code, and the RSP pointer will point to the address of touch1 at that point. Since we have only return instruction in the injected code, we will return and go to the touch1 function. Let's try it. And as you can see, we have solved level 1 again, but this time we have used code injection. Now we are ready to solve level 2. First, we need to update the last return address. Let's open our disassembled file and locate touch2. Again, we need to reverse the order of the bytes because of little endian. The return address is now touch2. Now we need to make sure that we call it with the correct argument. We can use the pop RDI instruction to put the correct value into the first argument register. The hexadecimal code for that instruction is 5F. Also, don't forget to remove 1 byte from the padding. Since this instruction will be executed immediately before the last return, we need to put the value, first argument's value here. And that value should be our cookie string. Again, we need to remove the leading 0x and reverse the order of the bytes. And finally, the pop RDI instruction accepts 8 bytes, so we need to fill the larger digits again. Now let's try. As you can see, we have successfully solved level 2. In the final section, we will solve level 2 again, but we will use return-oriented programming instead of code injection. So instead of returning to injected code here, we will find a gadget for pop RDI instruction and use it for our purposes. So we can remove the injected code and replace it with equivalent amount of padding. Now we need to find this gadget. As before, we need to start by disassembling the executable. This time we will inspect our target executable. Now we are searching for gadgets that we can use, and they are placed between start farm function and end farm function. So I will remove everything that's irrelevant here. Since this is the start farm function, I will select everything that's before it and remove them. Similarly, I will find the end farm function and remove everything that comes after it. Now this file contains the gadgets we can use. Since we are looking for pop RDI instruction, we will search for 5F. We have found a 5F instruction here, but the instruction following it is not what we want. We want to return after pop RDI. We are okay with 90 here because it's no operation, but this 92 breaks our plans, so we need to keep searching. Here, this is exactly what we want. This pops the RDI and then we can return after that. So let's open our exploit string and we will put the value in this, we will put the address of that instruction here. Also, before reversing these bytes, we need to increment the value by 2 because it's not the first instruction here. There are 2 instructions before it. So if we increment this by 2 in hexadecimal, we will get DF. Now we can reverse it, and then we need to fill the remaining digits with zeros so that it's 8 bytes. Now our gadget should be ready. Now we will run it on our target this time. And as you can see, we have solved level 2 with return-oriented programming. As a final note, please keep in mind that the return-oriented programming won't be as easy as this in the real assignment, because you may not be able to find the exact instruction that you are looking for in the gadget form. Instead, you may need to pop the value into another register and move the value from that register, or you may even need to move the value between several registers before you can get what you want. And with that, we have reached the end of the video. Thank you for watching, and I hope this was helpful.